Well, we'll now look at a double slit again, but now we will take into account the width of the slit. Before we had treated them as essentially point-like openings, or at least very, very narrow openings that could be approximated with almost a point. We'll see the approximations in this that are made as well. But first let me set up the geometry. Again, we've got two slits, and now they've got finite width. Again, we're looking down from the top. I've got everything centered up, and so the distance between the centers of the two slits, I'm calling that A. That's fixed for a given double slit. And then the width of each slit is B, so both of them have the same slit width, B. Again, I choose my coordinates, I think I called it Y, upward this time. And so I can locate, with respect to this 0Y at the center here, I can locate the edges of the right and the left slit, or the top and the bottom, as the case may be. You'll see that if I look at this edge up here, that it's going to be A over 2 plus B over 2. And the bottom one is going to be minus y equal to minus A over 2 plus a minus B over 2. So I get that for the two tops. And then this one may be a little bit less apparent, but the best way to write it is in terms of the distance to the center is A over 2, but now I'm going to subtract this half width, so it's A over 2 minus B over 2 is this top of that one. And then down here is just the negative of that, really. It's the total distance to here is minus A over 2, but I need to subtract to get back to here this half of the width, which would be minus a minus, so it would be add B over 2 to it to get to this point. Or another way to look at it, once I found this one, then the other one is just going to be the negative of it, so it would be negative A over 2 plus B over 2. I'll again assume that we've got plane waves incident on this double slit pattern. So they come in through here and go through the slit, and they're all in phase. Again, the way you realize that is a point source of a fixed monochromatic point source of wavelength lambda is far enough away so that it starts off as spherical wavelets, but by the time it gets here, they're nice planar waves in the Fraunhofer approximation. And then likewise, if I look at any given portion of this, the amount of wave that gets through this little piece dy here, that's a height y above the center, is proportional to the incident, the total incident wave amplitude. And we look at that as a point source of spherical wavelets again, and by the time it gets over to our detector at P, it's a plane wave approximation. So again, the detector's far enough away, and the source of the light that we're using, that's monochromatic, are both very far away, many, many, many wavelengths, and so we're in this Fraunhofer approximation valid range. The detector, again, I'm assuming it can rotate about the center here, and that's the very center of the two slits, in a circular fashion at fixed radius. And let's see what else. And then if you look at that, this is far enough away that I call this distance actually from this little place, the source of this one spherical wavelet, R1. And if you look at it like we've done before, we can think of this as like marking out a circle at this point, an arc. And so that arc length is very, very nearly perpendicular to both of these. And so, or you can think of this as dropping the perpendicular here. And this distance here, delta, is this distance when I drop the perpendicular. These two distances are the same from this point on. They're both R1. And this angle is theta. And so R1 should be the total distance, R, from the center to the detector, minus this small piece down here, which is delta. And again, I can draw this little triangle from my dy, drop the perpendicular here, over to here, to here, and that again is this. If this angle is theta, then this angle here, this is a 90 degrees, so this angle is 90 minus theta, so this one is theta. And again, we get that sine of theta is delta over y, so delta is y sine theta. And now then, the spherical wavelet from just this little piece here, by the time it gets over to the detector, looks like this. This is just our usual spherical wavelet. We're assuming that the amplitude that the wave is proportional to the thickness. So that's the amount of wave that's in there, I guess, is that. Proportional to that. Spherical wavelet, and this is by the time it travels this distance r1 from this point source, essentially, spherical wavelet all the way over to here, to the detector. And again, we make the substitution R1 is R minus delta. When I do that, I get this expression. I can again write the I kr minus omega t and separate out the delta term, now with a minus sign, I, and then delta is y sine theta. So this term, the I k delta, becomes this with a minus sign. And then again, ignore delta compared to this much, much larger distance. So again, out to 7 or 8 decimal points. So we've got really an approximation in the Fraunhofer regime on for the electric field at the detector. Now that's just for that one little piece right here. So I'll need to add up all the pieces, but just in the hole regions, just where the slit is. So I need to add up all of them, superposition principle, so that's just the integral over the whole slit openings of this factor. There's lots of constants here, or at least as far as the y integration is constants. E naught and r, I can pull those outside. This e to the ikr minus omega t, pull it outside. And I've got really a pretty easy integral to do. The only difference, or the only complication, is I'm integrating it over just the slits. And so I can integrate it over the bottom slit when y goes to minus a plus b over 2 to y equal to minus a minus b over 2 of this quantity. And then I add that, the integral over the top slit, which is y goes from a minus b over 2 to y equal to a plus b over 2. And those integrals, again, we've done these before, same thing. A little bit different than I've got a minus sign here, that's part of this constant, and that I have to evaluate at the upper and lower limit. And this one over here, again, a minus ik sine theta, evaluated over upper and lower limits. And then plugging those in, upper limit I get this, the lower limit I get this one, upper limit up here I get this term, lower limit I get this one. I factored out this minus ik sine theta because it occurred in both of these, so I factor it out. And I get these two turn into these four terms. From the first one, I notice I've got an ik a over 2, an ik a over 2, so I factor that out. It should be a sine theta here, ik a sine theta on that term. But I factor out that ik a sine theta. And I'm left with the b term. And that's going to be minus ik b over 2 sine theta. And from this one, again, should be a sine theta here, so make sure to put that in your notes. I get a minus, which is a plus. So I get a minus plus ikb sine theta over here. This one, similar. But if you look at it, I've got a minus ik a over 2 in both of these terms times the sine of theta. So I pull it out, I factor it out of both of these, and I'm left here with minus I k over 2b sine theta. And from this one, when I pull out the so when from this one over here, when I pull out the minus ik, I've got a minus, which is a plus ikb over 2. So similar in both of these. And now then, just so to keep from writing so I don't leave things out, I let alpha be ka over 2 sine theta and beta kb over 2 sine theta. And then I've got e to the I alpha, e to the minus I beta, e to the plus I beta, e to the e here to the minus I alpha, that's this term, that's this one. And I've got e to the minus I beta, e to the plus I beta. So just using this notation and substituting up here. And then what did I do? Oh, then I multiplied through by I on the bottom, so that puts it 1 dividing this term, 1 dividing this term. And then I multiplied by 2 and divided by 2, so I get a 2i and 2i here when I bring that inside. And that's just because I can see now that these are sine of beta. So now I get e to the I alpha, sine beta, e to the minus I alpha, sine beta. Or if I factor out the beta, I get sine beta. I get e to the I alpha plus e to the minus I alpha. And then I multiplied by 2 and divide by 2 so that I could call that cosine. So I get this expression, e naught over r, 4k sine theta. And then finally, I realized that this is almost like a diffraction pattern for a slit of width b. If I multiply by b over 2 on the bottom and b over 2 on the top, and when I do that, I get kb over 2 sine theta, which again is beta, and I get 4 times b over 2 here. So I've taken this inside. And so that gives me 2 e naught b over r cosine alpha times sine beta over beta. And here alpha is k a over 2 sine theta, beta is k over b sine theta. And then it's the same story. Get the irradiance or the time averaged intensity is just the 1/2 plus c epsilon naught times e squared. In this case, I've got it all down to real. And so I square this. That gives me 4 e naught squared b squared over r squared. Can you get this 1 over r squared fall off with the intensity of the irradiance? You'll get a cosine squared, and you'll get the sine beta over beta squared. Again, all of this we can lump into a single parameter, which I usually lump in as a naught. Notice as b is the slit, that b is the slit width. So as they get very small, then this intensity out here gets smaller and smaller as b squared. Or as e naught, the brighter the source is, well, the bigger e naught is, and so the brighter the source increases the intensity, as you would expect. In any event, we lump these together because those are all constant terms for a given experimental setup. And so we get the irradiance is I naught cosine squared alpha times this sinc function squared of beta. And if you look at these, the ultimate curve is the dark line. This envelope, I kind of think of this I naught times this part as this envelope. It's always positive. And then superimposed on that, I've got this higher, more rapidly varying one. I get the cosine squared of alpha. And the way I kind of look at these is we have two things going on. We've got single slit interference proportional to cosine squared alpha like we had before. And due to the finite slit width, we've got the single slit diffraction pattern. So these are going on simultaneously. And when you superimpose both of those, you get this characteristic pattern for a double slit that looks something like this. Well, we'll look at some implications of this maybe next time, but that's probably enough to digest in one setting anyway.